This is Lab 05 pressure. I'm going to go over the Lab 05 problems in this lecture. First problem, a tank with square cross-section measuring 11 by 11 meter is floating in water. The tank is filled with oil and air with the given density for oil and the given air pressure respectively. The oil height is 2 meters with the density of 800 kilogram per cubic meter. The pressure outside of the tank at point A is P sub A 101 kilopascal. The equilibrium conditions have been reached for the floating tank, and your tasks are to calculate the distance h given in the problem. And there's some hint here that I give you a hint here. If the tank is, it starts right here. The tank is floating in water. Thus, the pressure at point B, P sub B, at the very bottom of the floating tank is equal to the pressure at point C, P sub C, just outside the tank in water. So, from the principles of fluid mechanics, it should be pretty clear to you that the pressure at the bottom of what will be the pressure at this point, right at the bottom of the air, just above the oil at this particular point. Also, the pressure right at point B, and then pressure at point A, and also pressure at point C. And the rho of the water is given as 1,000 kilogram per cubic meter. That's also given. And we try to actually solve this particular problem. I'm going to provide you with more hints. As you know, at the bottom of this tank, at point 1, the pressure would be 150 kilopascal. This is air. The tank is full of air. It is a little bit pressure. This is more than the atmospheric pressure, but we are less concerned with that. Our concern is, first of all, calculate what would be the pressure at point 1. Secondly, what will be the pressure at point B? Since the equilibrium has been reached, the pressure at point 2 and pressure at point 3 is the same. I keep referring to these points as B and C because the given problem is actually given as B and C. Here I convert a little bit to 1 and 2 and 3 for clarity, but you can pretty much compare that and come up with the solution to this problem. So at point 1, the pressure would be 150 kilopascal. Again, that's right above the oil. At point 2, obviously we need to add a pressure at point 1 to the pressure that's caused by the oil, and that is rho GH, pretty much the height of the oil multiplied by the acceleration of gravity G and multiplied by the density of oil. In some books, rho is shown as gamma, sigma, whatever other type of Roman numerical. But here, as you can see, we're just dealing with rho. So rho times G times H, that would be the pressure of the oil at the bottom of the tank. We need to add the atmospheric pressure if it's open to air. In this case, because it's not open to air and it is actually there's a pressure of 150 kilopascal of the air present at point A. We simply add that 150 to the pressure that's caused by the weight of the oil, as I just pretty much described it here. So we add that to the 150 kilopascal pressure. That's simply 800 kilogram per cubic meter. That's the density of the oil multiplied by 9.81, which is the center of gravity meter per square second or second squared, depending on what you would like to call it. And that will be giving us the pressure at point 2. So we have the pressure at point 2 now. And the question is, how do we calculate H. Remember that equilibrium has been reached. So the pressure at point 2 and pressure at point 3, they must somehow be related. I'm going to give that information out to you toward the end of this particular problem. So what does that mean? Equilibrium has been reached. That's the trick here. What does that mean in terms of pressure at point 2 and pressure at point 3? Is one is greater than the other? One is smaller than the other? Is it equal? So that's the question that you keep in your mind, and hold on to that question until we get to it shortly. So this is pretty much P sub 2 pressure at point 2. Let me go back up to the pressure outside the tank in the water. And that's pressure at point 3. Pressure at point A is the atmospheric pressure, right? Point A is given up here. At this point, since this is exposed to air, although the pressure at here is different than the pressure 150 kilopascal inside the tank, this is pressured air, and this one is atmospheric pressure. So pressure at point A is really the atmospheric pressure. Depends on the geographic location of a particular point, and that pretty much translates to the elevation from the sea level. The pressure varies according to that. So outside the tank at point 3, the bottom of the floating tank, P sub 3 would be atmospheric pressure plus the column of water that does present. This actually is presented above point 3. That is really basics of fluid mechanics. Every time you have a column of a fluid, and if you would like to calculate the pressure at the bottom of it, for example, for this particular shape that I'm showing you here, the pressure, assuming that the pressure up here is 0, the pressure at the bottom would be nothing but rho g h. So h would be the height. So this is really the h. Okay. So you multiply that by the density of the fluid times acceleration of gravity. That would give you the pressure at this particular point right here at the bottom of this column. With air, this is not true, and that's with the fluid. Air is an exceptional case. If the air is not pressured, obviously the pressure at point O, at this level O, is the same as the pressure at the bottom H. If this is only filled with air and there is no pressurized or there's no gradient, pressure gradient from all the way down from the top of H to the bottom. So that's really all that is there. So P sub 3 would be P sub A plus rho g h. In this case, the H would be H plus 2, right? This is the entire H. The total H that I'm talking about would be this H that's given in the problem, plus 2. So this would be H plus 2 multiplied by G and multiplied by rho of water is 1,000 kilogram per cubic meter. To that, we're going to add the pressure at point 8, which is the atmospheric pressure. The assumption here is that P sub A is the atmospheric pressure. It's 101 kilopascal or 101 kilonewton per meter squared. That's the definition of Pascal is Newton per. So that's really what's really involved here. look that up. What is the definition of? It's a good time to review that. So what is the definition of a Pascal? It's what is a Pascal? And make sure you guys understand it. You can also check that. What is a Pascal? How can you come up with that? You can look at the formula here, and since we can only add apples to apples and oranges to oranges, this one is 101 kilopascal. And we have 1,000 kilogram per cubic meter times meter per second square times meter. So it's going to be kilogram per, as you can see, if this drops out, and here you're going to end up, it's a meter here, and there's a meter here, so it's a square meter. You're going to have a kilogram per meter second. You're going to have kilogram divided by meter multiply second square, right? That would be 1 Pascal, okay? So anyways, that was the main point. The main point here is how to calculate the point at, to calculate the pressure at a particular point, in this case, point 3. So we are going to have an equation with the answer expressed in terms of a number plus 9.81 times 10 to the power 3 h. And that's also important to realize. So P sub 3 is expressed in terms of h. And from this point on, in order to calculate what we need to calculate, right, which was the distance h, we need to find P sub 3, which we did, and we express it in terms of h. Now we need to find another condition, so we can find what h is. I don't want to give the answer out to you. I want you to try this, but the trick is P2 and P3 in equilibrium. Is P2 greater than P3? Is it smaller than P3? Is it equal to P3? And I don't have much really further discussion about this particular problem, except telling you that P sub 2 is equal to P sub 3. That's the trick. In order for the inside tank to be floating in water, this is the inside tank that has been shown here. In order for this particular tank to be floating in water, a pressure at point 2 must be approximately must be the same as P sub 3. Don't forget that word approximately. It may not be 100%, but 99%. For the sake of our discussion, that's a good accuracy that we use. So P sub 2, you equate P sub 2 to P sub 3, and really that's a simple arithmetic from that point on, and you can calculate h. Let me move on to the second problem. The single tube is filled with a variety of liquids of different densities. It's a very interesting problem. It really tests some of the principles that are used in some of the mechanical pressure measurement devices. You do not do too many of the pressure device measurement for this particular assignment, for this particular lab. You are basically doing 2 numerical problems for this lab. And I rely you guys to go ahead and read the book. Remember, my lectures and book, they are complementing each other. I'm not going to cover everything that's in the book, and the book is not covering everything that I present to you here. So you need to look at the lectures and you need to also study the book, the appropriate chapter. Make sure you understand that. And if you have questions, please let me know. So a single tube is filled with a variety of liquids of different densities. This problem has two parts. Part A, what is the difference in pressure at A and B for the figure shown below? And then what's the pressure at B? What's the pressure at A, knowing the pressure at B? So if you can solve part A, part B would be a really simple calculation from that point on. You are going to find what P sub A minus P sub B is. You know P sub B, and then you're calculating P sub A. So the way I see it, we kind of like move from one point to the other. So I'm going to move from A all the way down to point 1. From point 1, I'm going to move up to point 2 along this tube. It's kind of like I'm moving in this direction. Okay, I'm going down, then I'm going to go around and calculate the pressure at point 2. Then I'm going to pretty much continue and calculate the pressure at point 3. I butchered the shape really. Let me see if I can get you a clean figure now. I need to clear all that up. There we go. So I cleared it all up. So as you can see here, again, I'm moving from point A down to point. Oh, sorry, I need to clear all that. And then I go to point 1. From 1, I move up here. I'm going to go to point 2, and from 2, I'm going to go to point 3, and from 3, I'm going to go to B, and then find P sub A minus P sub B. That way, if it turns out to be negative, then that means greater at 1. The pressure at A would be greater, and vice versa. So P sub 1 minus P sub A is really, again, using the same principle. These are liquids of different densities, and the pressure, the difference between point 1 and A, not knowing, for example, what pressure at A is, assume it as P sub A. So P sub 1 minus P sub A, which is nothing but the pressure at 1 in this case, is rho sub 1 G L sub 1. Rho sub 1 is given 1,000 kilogram per cubic meter multiplied by G, 9.81 meter per second squared, multiplied by L sub 1, which is 0.5 meter. Instead of just punching the numbers at this point, do a number crunching right away. Instead of the number crunching that normally you would do, what I would do is I'm going to continue this down the path and see if there's anything I can do to eliminate some of these some parts of the equation that can cause more calculations. I'm trying to see if I can eliminate that just going through more equations. So knowing the pressure at point 1 in order to calculate the pressure at point 2, between point 1 and point 2 there's a pressure difference. P sub 2 minus P sub 1 again would be nothing but rho sub 2, which is the blue liquid that's given, multiplied by G, multiplied by L2, since the distance between point 1 and point 2 is given. If this wasn't given, if P sub 1 minus P sub 2 was not given, then it would have been more difficult to calculate that. So L sub 2 really help you. Forget about how many tubes you have between point 1 and 2, what the shape would be. The difference between the difference in pressure between point 2 and 1, if you can identify L2 and you can know, if you know the density of the liquid that contains the pretty much, if you know the liquid of rho 2 in this case, the blue liquid, then it would be pretty easy to calculate using the same principles of fluid mechanics that we just described. So P sub 2 minus P sub 1 is rho sub 2, this is rho sub liquid 2, which is the blue liquid, multiplied by G multiplied by L2, which is given, L sub 2 is the distance between 1 and 2. That's really what's really important here when you do this kind of a calculation. So pressure at point 2 and the pressure at point 1 is pretty much calculated. Now, if we want to go from point 2 to 3 and calculate the pressure gradient from point 2 to 3, we follow the same thing. We identify the height, we identify the difference in elevation from point 2 to 3, and then we continue using the same method that we did for calculating P sub 1 and P sub 2. So P sub 3 minus P sub 2 again would be rho G, the difference in elevation would be L sub 3. So that would be rho sub 3 G L sub 3. Rho sub 3 is the yellow liquid, the density of the yellow liquid that is presented to you here. Then if we would like to calculate the pressure difference between point 3 and P sub B, we would follow the same procedure, knowing L sub 4 and knowing the density of the gray liquid, in this case rho sub 4, and we simply multiply rho sub 4 G times L sub 4, and that would be the pressure difference between the point B and 3. So what about now if we want to calculate the pressure difference between point 1 and let me switch this to highlighter and let me pick up the color. It's easier to see. So what if we want to go from point A to point B and we want to calculate the pressure? And if we add all this together, we should be able to have an equation for that. So P sub 1 minus P sub A plus P sub 2 minus P sub A plus P sub 3 minus P sub 2 plus P sub B minus P sub 3. If we add them all up, this term P sub 1 would drop out with this term P sub 1. So this is going to drop out. This is going to drop out. P sub 2 would drop out with minus P sub 2. P sub 3 would drop out with minus P sub 3. And all we left is P sub A and P sub B. So from here, you can easily calculate. If I add all these up, P sub B minus P sub A could easily be calculated. Then knowing the pressure difference between point A and B, and knowing the pressure at point B, pressure at point A could easily be calculated. That's really all to this problem. If you have any questions, feel free to contact me via mehraba, MEHRABA @DaytonaState.edu. Thank you.